Hi ladies, this is lesson 7.3, and in this lesson we're looking at functions involving e. Now this e is not a variable, it's a constant term. It's kind of like pi. So our first vocab term, natural base e. So this e is called Euler's number. And again, it's a constant term. It's not a variable. It actually has a value. And it's approximately equal to 2.72. Like pi, it's also irrational. And it's referred to as the natural base. So natural base E, natural base, it's irrational, and it was discovered as we look at as x approaches, or as n approaches infinity, as some number approaches infinity, 1 plus 1 over n all to the n power approaches this number. And that's E. So we're going to use this natural base like a variable, like we would with any properties of exponents like we've worked with in the past. So first we're going to simplify these expressions. So here our base is the same, e is the base in both of these, and we're multiplying. That means we add the exponents. In the second one, this is like saying 18 over 2 times e to the 6th over e to the 4th. Again, we're just applying these rules to the exponents that we've worked with before. So that's 9 times e to the 6th minus 4 power, because we're going to move that e to the 4th to the numerator, and when we do that, it changes signs. So we have 9 e squared. And then the last one, we're taking power of powers. So we have to distribute that exponent to each term that's being multiplied. So we have 4 squared times e to the 3x times 2. So that's 16 times e to the 6x power. Now, since e actually has a value, again, it's not a variable, it's a constant term, it actually has a value approximately equal to 2.72. We can actually evaluate these expressions. So on your calculator, you can evaluate these expressions. So e to the negative 2nd power, you'll find that if you hit the second key, and then you actually have an e to the x power. And then you'll enter -2 and hit enter. And that's approximately equal to 0.135. And then the second one, e to the 0.3 power. Again, you can do that on your calculator because e actually it has a value. So second, e to the x, and we're looking at 0.3, which gives us approximately 1.35. So now try these on your own. You're simplifying, so e is in your answer still. You're not evaluating, you're simplifying. So pause the video while you work, use properties of exponents to simplify, and you can unpause for the solution. So in the first problem, you're multiplying numbers that have the same base. The base is e, so you add those exponents, and you can simplify that expression as e to the third power. And in the second example, you have a couple components. First, you have to distribute this second exponent to both terms inside the parentheses, so 4 squared times e to the 3 times 2 power, which is e to the 6th power. 4 squared is 16. And then your denominator, 8 e to the 5th. You can simplify this by moving this e to the 5th to the numerator, and when you do, you subtract the exponents. You have the same base, so you have 2 times e. For the second part here, now we can use a calculator, and we're actually evaluating these expressions. So again, e is an actual number. It has a value. It's an irrational number, so we can actually evaluate these. So e to the negative 4 is approximately 0.018. And then e to the 0.36 power is approximately 1.433. All right, now let's look at these functions involving e. So when we graph these, it's not really any different than how we've done it with a variable, except that now it's not a variable, it's a constant term, so we can actually plot these points. So a function of the form y equals a times e to the rx power is called the natural base exponential function. So in this exponential function, a has to be greater than 0 and r has to be greater than 0. And if that's true, then it's an exponential growth function. Okay, involving e, it's an exponential growth function. If a is greater than 0 and r is less than 0, then it's an exponential decay function. So you can see the two general graphs, y equals e to the x and y equals e to the negative x, where in the first one here, r is 1, which is greater than 0. And here, r is negative 1, which is less than 0, so it's a decay function. The asymptote for both of these is 0. It's the x-axis, so it's y equals 0. And then going a little bit further, if you look at your note sheet, that steps to graphing, notice the form a times e to the r times the quantity x minus h plus k. So when you're graphing these, first you're going to want to graph this function, a times e to the rx, and then you're going to shift it horizontally, h units, and vertically, k units. Just like we've done in the past, except you have this extra step here of that r value. And if it's greater than 0, it's a growth function. If it's less than 0, it's a decay function. So let's look at a couple examples. So again, shifting horizontally, h units, and vertically, up or down, k units. So let's look at an example. So the first step here, well, in this first one, we only have y equals 2 times e to the rx. So our a is 2, and our r is 0.6. 2 is greater than 0, 0.6 is greater than 0. So they're both greater than 0. That means it's a growth function. So now we can graph this just like we've been graphing. We're going to just plot those 2 points where x is 0 and x is 1. So when x is 0, we have 2 times e to the 0.6 times 0 power. So that's e to the 0 power. Which is 1 times 2, which is 2. And in the second one, where our x is 1, we have 2 times e to the 0.6 times 1 power, which is 2 times e to the 0.6 power, and you'll use your calculator for that. So 2 times e to the 0.6 power, which gives us about 3.64. Okay, so we can graph those points. So 0, 2, and we know that it's a growth function, and 1 and 3.64. Oh, let's move this over. So then we can actually sketch in this graph. And we can define our domain and our range. So here, our domain is all real numbers. And our range is y is greater than 0, because our asymptote here is the x-axis, so it's never going to touch the x-axis and it's never going to go beyond the x-axis. All right, now in the second one, we have our function here, but then we also have an h and a k value. Okay, so let's look at all of our pieces of our graph first. So we have a is equal to 1. Our r is equal to negative 0.35. And then we'll look at the h and k in just a second. But with these two pieces of information, if you look at your key concept, it says if a is greater than 0 and r is less than 0, then the function is an exponential decay. So here we know that this is an exponential decay function because this is less than 0. So that tells us it's an exponential decay function. Now next, we're going to look at the h and k value. So the h value in this case is -1 because we have x plus 1, which is the same as x minus -1. And our k value is -2 because we're adding -2 to that function. Okay, so that means that we're going to shift our graph 1 unit to the left and 2 units down. But first we need to actually graph that first function, y equals a times e to the rx. So I'll put this in a different color. So first we're going to graph y equals a, which is 1, times e to the rx, negative 0.35 x. And when we do that, we're going to pick 2 points, 0 and 1. So when x is 0, our y value is e to the 0 power, which is 1. And when x is 1, our y value is e to the negative 0.35 power, which we'll do on our calculator. E to negative 0.35 power is 0.7 approximately. Okay, so let's plot those 2 points first. 0, 1, and 1.7. Again, we know this is an exponential decay function because our a value is greater than 0, but our r value is less than 0. So we're going to sketch our graph in, and then we're going to translate it. So we're going to translate it to the left 1 unit and down 2 units. So to the left 1 unit and down 2 units. Our asymptote goes from here down 2 units. So now it's at y is negative 2 instead of y is 0. Okay, so we can sketch in this graph here. And define our domain and range. Domain is all real numbers, but range, since we shifted the whole graph 2 units, instead of being y is greater than 0, we have y is greater than negative 2. Because again, we shifted the entire graph down 2 units. That was our k value, negative 2. So try this one on your own. You can pause the video while you work. Again, you're going left or right h units and up or down k units. You should graph this part first and then translate. So first you want to graph that y equals 2 times e to the 0.7x. And you know that a is 2, r is 0.7, so you know it's an exponential growth function. After you have graphed that, you chose points 0 and 1 for your x values, and then evaluated your y values. After you've graphed that, then you translate. So now you can identify your h value as 0, which you can see from here. 0.7x is the same as 0.7x plus 0, plus 3, which is your k value. So k is equal to 3, which means we translate 0 units horizontally, but we move the whole graph up 3 units, including the asymptote. So it was at the x-axis, but now it's 3 units up. So we can identify our domain, all real numbers, and our range is y is greater than 3, because that graph stays above that asymptote of y equals 3. Domain is all real numbers, range is y is greater than 3. Now this next part deals with continuously compounding. So if you remember before, we talked about compounding as the number of times per year your interest is calculated, and we had this formula. The amount equals the principal times the rate, or times 1 plus the rate over the number of times it's compounded to the power of t years times the number of times per year it's compounded. Okay, so this is our compound interest formula. But if you remember, as your n value approaches infinity, quantity 1 plus 1 over n to the n power approaches e. Okay, so it gets closer and closer to e. So we can use that e in this compound interest formula where we compound continuously, meaning like every second, multiple times every second, just constantly compounding interest. We're going to use that e value. So the a is still the amount in the account after t years, and p is still the principal. And r is still the rate expressed as a decimal. So when we compound continuously, that's just constantly compounding, not a specific number of times, but like infinite times per year. So if we deposit $3,500, we're looking for the amount in our account. If we deposit $3,500, that's our P value that pays 4%. And we're looking for it compounded continuously. So we're going to multiply P times E, and we're going to take E to the power of R, which is our rate expressed as a decimal, which is 0.04, times T years, which is 1. So 3,500 times E to the 0.4 power, which we can do on our calculator. 3,500 times E to the 0.4 power, which gives us $5,221.39. All right, try this next example on your own. You can pause the video while you work and unpause for the solution. So again, we're using that formula, A equals P times E to the RT power. So our principal is 4,800. Our rate is 0.065. That's our rate expressed as a decimal. And we're looking for continuously compounded after 3 years. So A equals 4,800 times E to the 0.065 times 3 power, which if you put that in your calculator, you get $5,833.49. So please jot down any questions you have and we can go over them next time I see you in class. Thank you.